Now we have finished talking about parameter adaptation algorithms with recursive least square derived all the way from the concept to the solution. Now comes to the question, that's actually once you get it, the implementation is very easy. Now let's talk about something that's relatively not so intuitive and sometimes may even feel counterintuitive. We have all seen this is the formula for recursive least squares, and this is actually the formula for general parameter adaptation algorithms, not just for recursive least squares, but also other things. And if you go a little bit beyond to optimization theory, you will see this kind of formula is also very common. But the more you look at it, the more doubts some people may have. Because this is really adding a lot of things. You see, we are forever adding some terms to this parameter estimator theta hat, right? If you think about what is inside here, you can appreciate that this can be even more. If you think about this, what is happening inside, you can even appreciate more that this might be really potentially leading to something that won't converge. You remember this forgetting factor k, right? We initiated at a very large number, okay? And the update of this forgetting vector, of this adaptation gain, is that it's always going to be symmetric. Actually, it's going to never be exactly 0. And then these are just data vectors, data parameters. This is an error term. This might fluctuate around, and it must be fluctuating around in the end perfectly so that this stays at precisely the true value. We want it to be approximate to the true parameter as k go to infinity. So this is not really trivial, and sometimes it's not really guaranteed. And there are two things here, actually. There is the concept of stability, the concept that this does not blow up. And then there's another concept, convergence. We want it to not only do not blow up, but also we want the parameter to go to the true value. So two things here that are important. So stability is the concept we're going to talk about today. And then we're going to talk about convergence next time. That's the first motivation. Now the second motivation to think is this is not really something that we can easily use finding out the poles or zeros or eigenvalues of the system. That doesn't exist. Look at this. There's no way that you can easily find out the poles of a so-called system here. So we needed some new tools. This is actually, the whole adaptation is actually a nonlinear system. So the tools that we're going to use there are two possibilities to talk about stability. One is to use Lyapunov theory. And another is to use hyperstability theory. Both theories are stronger than regular linear time invariant system stability theory. Okay, so roughly speaking, if a system is hyperstable, then it's going to have a stronger condition than just a normal LTI stability. We're going to focus on hyperstability theory for this class. All right? Most of you have experienced Lyapunov stability before, and, but not everyone has background about this, so I will use hyperstability. And the basic concept is as follows. Let's call two systems. They can be linear or nonlinear. Then the concept of passivity and strict passivity is very useful here. Roughly speaking, if we say a system is passive, let's say here, if we say system 2 is passive, roughly speaking, we're saying this system does not generate energy. I'll explain the concept a little bit more using going one more step further. Strict passive, if we say a system is strictly passive, that means the system will dissipate energy. All right? So, for example, if we have a moving mass, if the surface is frictionless, then no energy is generated. It's going to move around. The total energy is conserved. If there's friction on the surface, then eventually energy is going to reduce to zero. And then this system has the concept of strictly passive. And if you think about, you can already imagine the connection of strict passivity to stability here, right? If a system is strictly passive and you supply, let's say, if this system is strictly passive, it's going to consume energy. And if your supply the energy does not keep increasing, then eventually all the energy is going to reduce to zero. And then the state of the system will become going to zero as well. And we have stability. All right? More formally, there are some terminologies we introduce. Centered around passivity and strict passivity, we have two concepts. So, for linear system, the concept of passivity relates to a terminology called positive real. And then if it's a nonlinear system, the concept of passivity becomes relevant to the terminology of a Popov inequality. The terminology mainly comes from the person who invented the concept. So Popov was the one who introduced hyperstability, and the concept passivity is framed in his theory called Popov inequality. In linear system, there is a concept of positive real to talk about passivity. The framework of hyperstability actually goes a little bit more. This is too general. This is very, very much general. The way that we use hyperstability for adaptive control and system identification is as follows. The way that we frame the block diagram as follows. We frame this feedback system where the top system is a linear time invariant. The bottom part is nonlinear. All right? So for the linear time invariant block, we use our conventional either state space transfer function. So we have, if it's a continuous time system, then we have the usual ABCD matrices for the state space system. And if it's a discrete time system, we would use the normal discrete time framework. All right? So the concept of hyperstability, the goal, so let me put X as a state over here. The goal for hyperstability is to eventually reach some nice behavior for state X. Okay? So that's the focus. Eventually, the nonlinear block will not matter so much, and we just want to have good properties for the LTI block with the state variable. Eventually, we want it to go to 0. So nice behavior of X is the target. So that's the LTI block. It's relatively easy. For the nonlinear block, that's where we introduce the concept of passivity in a little bit more formal term. We define a passive system to satisfy certain properties. The system has an input V and output W. We assume it's a square system, so V and W have the same dimension. So for the square system, with the same number of inputs and outputs, it is called passive if this inequality holds for the continuous time case. If we do the product between input and output, it's going to be lower bounded by some negative numbers. And the intuition is as follows. This is, if you imagine you apply a force, if you apply a force to a mass and then it has a velocity, then force multiplying with velocity and added integration is going to be the work you apply to the moving mass. So this is in a way saying that the applied work to the system will be lower bounded by some number. All right? So if you think about, the system has an energy. My energy in the end minus my energy at the beginning, it wouldn't be crazily large. It will be limited by the amount of work that I apply to the system. All right? So this is the work that I apply to the system. Okay? My terminal energy will not be crazily increased. Okay? It's going to be limited by the maximum I can achieve in the end. It's going to be my initial energy plus the work that I apply to the system. All right? It cannot be larger than that. If it's larger than that, that means the system somehow generated energy itself. So that's the concept of, that's why it is, if you flip the signs, you can compare the two equations. All right? This is the negative gamma square. So that's the intuition. If it's a discrete time case, it's going to be similar. Continuous time case is integration. In discrete time, it's going to be summation. So in discrete time, it's going to be K all right, so this is for any T1 and K1. Regardless of how you choose your terminal time, as long as your terminal time is larger than your initial time, as long as you do this integration, you're going to be limited by this sort of conservation of energy to be called the passive system. Let's do this to be a little bit more consistent. Yeah, but good catch. This is just passive. Now, the concept of strictly passive, it's similar. It's going to be a little bit more than just this. All right? So let's think about how to put strict passivity into equations. The same system. Strictly passive, or sometimes called dissipative. It dissipates energy. If it satisfies this condition, it's the same concept with a few more extra terms. The basic concept is, you see here is passive, all right? Strictly passive basically means remove this possible equality. It's going to put the constraint that in the end, the energy will strictly be reducing. And the way that is put in here is as follows. We have the same larger than equal to sign, and then added something that's going to become positive. So the way to write is add some term about the energy of the input, some term about the energy of the output. And the scaling sigma and epsilon are such that they won't both be zero. Maybe one of them can be zero, or maybe two of them are not zero. They cannot be both zero. So this is going to become something positive, and the effectively making this less than instead of a less or equal to sign. In all these cases, gamma related to initial condition. Yeah, so that is important. Okay, so these are the definitions. Something that's going to become not only intuitive but also rigorous in math. is this fact here. Let's say two systems, 1 and 2, are both passive. Talk about interconnections now. Then we can show that a parallel connection of the two systems is also going to become passive. If you run two passive systems together, it's going to become a passive system. And what's even more interesting is if you connect two passive systems together in a feedback loop, it's also going to become passive. All right? Let's work on these two examples, especially this one. I will work on this one, and then we will have some time for you to practice, understand this one. Okay? If you can't do this one, then you can see why this is going to become to make sense. All right? We're going to have two passive systems together, and the eventual system in a feedback loop is going to become passive. And interestingly, if one of them is strictly passive, then some nice behavior also going to occur to this feedback loop. So the first one, let's say I have two outputs I will call W1 and W2. Then, because system 1 is passive, so we are going to say, let's consider the continuous time case. It's going to be lower bounded by some gamma 1 square negative. And for the second system, we have the same structure of inequality. And W in the end is just W1 plus W2, so therefore we can add them two together. We have the new lower bound of negative gamma 1 square plus gamma 2 square. And effectively, we show passivity. So that's the general principle to do this. Now, I would like you to spend some time to look into the feedback connection, do some practice, and show mathematically why it's a passive system. All right? Sounds like you guys have obtained some conclusions. Any volunteers want to talk about how to do the feedback block?
Okay, so just looking at, let's call the input to system 1 W, which is V minus the output system 2.
Just a sec. Call system 1 input to be...
W, let's call it.
But I have W.
Sorry. U, yeah.
Okay.
Okay. And then so the output of system 2, let's call like Y2 or something.
Okay.
Okay. So let's just start with, we know system 2 is passive, so the integral of W transpose Y, sorry, Y transpose W is bounded.
Mm-hmm.
And then, okay, so we also know that system 1 is passive, so integral of W transpose U is also bounded.
Mm-hmm.
But U is V minus Y2.
Okay. V minus Y2.
Yeah. And then we can pull out the integral of W transpose Y2, which we already know is bounded.
Okay, so let's P. Pull out minus W Y2
And you can move that to the other side, that integral is
Alright.
pulled out.
Okay. Move it to the right. Oh. Minus.
And so now the left-hand side is greater than or equal to minus gamma 1 squared minus gamma 2 squared.
Okay. Right.
And that's the whole system, because WV is our input output.
Okay. Everyone agrees? Okay. So there's one step here. This is both larger than or equal to, but it's slightly different. These two larger than or equal to are a little bit different. Here, larger than or equal to, we use the fact that this is larger than or equal to negative gamma 2 squared. Okay? So strictly speaking, which one is going to be a little bit more larger than or equal to? This is square.
So that upper inequality is going to be a tighter bound on the overall thing.
Right. Right? So this is more tighter than this one. Some minor things to notice. That's the mass, and the result is really interesting, right? It is saying this kind of concept. I have two blocks. If I can show both of them, I just only need to show individually both of them are passive. Then I can guarantee the entire system is going to be passive. So we break a potentially more complex problem into two smaller problems. That's exactly the definition of hyperstability. So the definition of hyperstability is as follows. This feedback system, let's call this figure star, is hyperstable if and only if there exists constant delta and gamma, positive constant delta and gamma, such that So this is really becoming now focused. Remember, right? Our focus is on nice behaviors of the states. This is really talking about the states. It's saying for a hyperstable system, the state has this nice property of it's always going to be bounded regardless of the time, whether it's 1 second, 10 seconds, or 1 day, 1 year. The state is always going to be bounded by something dependent on the initial condition and some constant term. All right? It's never going to blow up. This is a bounded quantity. All right? It doesn't move with respect to time. It's a constant. This is for continuous time case. Or for discrete time case, we have a similar concept with just the difference in the notation for the state. All right, so this is hyperstable. The state is going to have this condition, and then this is for all. Effectively, it's saying this block is going to have this nice property bounded states for all passive systems in the nonlinear block over here. Okay, so this is the condition is the lower part, the feedback part, is a passive system. So this is for all feedback blocks satisfying this Popov inequality. All right, so effectively this is saying it's passive in the nonlinear block. But when Popov made these discoveries, he wasn't aware about passivity, the concept yet. This is for continuous time, and effectively for discrete time systems, it's the passivity definition, the summation here. So for discrete time, the Popov inequality is exactly this one. This is hyperstable. It's similar to the concept of being Lyapunov stable. We only have X to be bounded, but in practice, we often want a more stronger condition where not only are they bounded, but they eventually go to 0. So a stronger, even stronger condition is asymptotic hyperstability. The same thing, figure star. This feedback system is asymptotically hyperstable if and only if it is hyperstable and it for all bounded W satisfying the Popov inequality. We have the limit of the states. Either it's continuous time or discrete time. Eventually, all the states is going to become, is going to move to the origin. So the limit is going to become 0. Okay, so there is something subtle here. First, it has to be hyperstable. So that means we need to have this Popov inequality. We need to show the bottom block is actually passive. And second, there is this condition that W needs to be bounded. So the block, let's redraw. The signal notations actually are relevant. So the feedback channel signal must be bounded. Okay? Effectively, that's saying we shouldn't put something that's infinity to the linear time invariant block here. Then the system is going to be hyperstable, asymptotically hyperstable, with all the states going to 0. All right? So that's what the major thing today. We introduced some definitions. We talked about the concept and principle of stability analysis, and we connected to feedback systems, how we're going to use the theory to analyze more complex systems.